In this series, we've talked about what endpoints are, how they are identified, what roles they play, how their state changes, how independent they are, and how long they exist. Now, we are going to focus on something that sounds simple but quietly defines whether a network is useful at all: endpoint availability. Endpoint availability describes whether an endpoint can be reached and can respond when it is needed. At a basic level, it answers one question: is this endpoint available right now? But in real networks, availability is not just on or off. It exists on a spectrum. An endpoint may be fully available, partially available, intermittently available, or technically reachable, but practically unusable. To understand endpoint availability, it helps to use a simple metaphor. Think of an endpoint like a shop. Availability is not just whether the building exists, it is whether the shop is open, staffed, stocked, and able to serve customers. A shop with locked doors is unavailable. A shop that opens randomly is unreliable. A shop that opens on time but cannot serve customers is technically open, but functionally unavailable. Endpoints behave the same way. At the most basic level, availability starts with reachability. Can the network locate the endpoint? Can packets reach it? Does it respond to basic requests? If the endpoint cannot be reached, it is unavailable, regardless of what services it is supposed to provide. But reachability alone is not enough. An endpoint may respond to network probes, but fail to deliver meaningful service. A server that accepts connections but times out under load is reachable, but not available in practice. This is where availability becomes a behavioral concept, not just a technical one. Endpoint availability depends on capacity. Is the endpoint able to handle the volume of requests it is receiving? Is it overloaded? Is it throttling responses? From a network's point of view, an overloaded endpoint is only partially available. It exists, but it cannot meet demand. Availability is also affected by dependency chains. An endpoint may be healthy on its own, but depend on other endpoints to function. If a database endpoint becomes unavailable, application endpoints that rely on it may also become unavailable, even though they are still running. This is why modern networks treat availability as a system-level property, not a single device metric. Endpoint availability is deeply tied to time. Some endpoints are expected to be available continuously. Others are only available during specific windows. Some appear only when triggered by events. A backup endpoint may be unavailable most of the time, and that is normal. A public-facing service endpoint is expected to be available almost always. Understanding expected availability is just as important as measuring actual availability. This leads to the idea of availability targets. In professional networking, availability is often expressed as a percentage. 99% availability, 99.9%, or higher. These numbers represent how much time an endpoint is expected to be available over a given period. Small differences in percentages represent large differences in real-world behavior. An endpoint that is unavailable for minutes per year behaves very differently from one that is unavailable for hours. Endpoint availability also shapes network decision-making. Load balancers distribute traffic based on which endpoints are currently available. Routing systems avoid paths that lead to unavailable endpoints. Monitoring systems continuously evaluate availability and trigger responses when it degrades. Availability is not just observed, it is actively managed. From a security perspective, availability is one of the core goals of networking. A network that is secure but unavailable has failed its purpose. Attacks that target availability, such as denial of service attacks, aim to make endpoints unreachable or unusable, even if they are not compromised. This is why availability is often discussed alongside confidentiality and integrity. Endpoint availability is also closely related to redundancy. Instead of relying on a single endpoint, networks often deploy multiple endpoints that serve the same role. If one becomes unavailable, others can take over. This is like having multiple shops instead of one. If one closes, customers can go elsewhere. Redundancy does not eliminate failure, but it limits its impact. In modern cloud and distributed environments, endpoint availability becomes even more dynamic. Endpoints are created and destroyed automatically. Traffic shifts constantly. Failures are expected, not exceptional. In these environments, availability is maintained not by preventing failure, but by responding to it quickly. Endpoints are replaced instead of repaired. Traffic is rerouted instead of delayed. Availability is preserved through motion. This changes how we think about networks. Instead of asking whether a specific endpoint is always available, we ask whether the service remains available as endpoints change. Endpoint availability, in this sense, is about continuity of behavior, not permanence of components. Understanding endpoint availability helps explain many network behaviors that might otherwise seem confusing. Why traffic suddenly shifts. Why connections are dropped and retried. Why systems prioritize some endpoints over others. Availability is the signal that tells the network where it can safely send traffic right now. Endpoint availability is not a single metric. It is the result of reachability, capacity, dependencies, timing, and design. It reflects how reliable an endpoint is as a participant in the network. And in the end, endpoint availability is what turns a network from a collection of connections into something people can actually depend on. That is endpoint availability.